Hello, friends. It's a beautiful morning here. I hope everyone is doing great. My name is IBM, and I am here to give you another episode of Learning Physics. Do not forget these are solved past paper questions for AS Physics, that is paper 2, AS Structured Questions. And this could be the last part of dynamics, that is uh, considering Newton's laws of motion and linear momentum. Do not forget, as I mentioned earlier on, that the questions in most of these AS units do not have a clear boundary as the topic is concerned. Some questions overlap from one topic to another topic. Therefore, you may not find a clear boundary between questions of dynamics and questions of kinematics or questions of work, energy, and power. So there will always be overlap, and therefore you should just bear with this. Do not forget to subscribe, share the videos, or download them and view them at your convenience. Do not forget to download the document in the video description so that you can always refer to it. It's better to watch the videos with a hard copy of the past paper question so that you follow on a hard copy rather than just watching the videos. So without wasting any time, let me take you to part 3 of dynamics. Part 3 of dynamics. I think in part 2 we must have stopped on page 172. You can, if you have a document with you, you can verify. And I want us to move straight away to page 173. And this is our first question. Define acceleration. I think acceleration was defined in kinematics, but since there is no clear boundary between these units, we shall redefine it here. Acceleration is the rate of change of velocity. Rate of change of velocity. There is always no need for you to start answering a question by quoting part of the question. You can just start by answering the question. Rather than saying acceleration is, you just say rate of change of velocity. When I talk about rate of change of velocity, I mean change in velocity over time. Change in velocity over time taken. Now, many times we make a mistake and fail to define such simple concepts by failing to understand that acceleration is change in velocity, because when velocity does not change, then the acceleration is zero. So when you say acceleration is velocity over time, then that is not acceleration because velocity must be changing. State Newton's first law of motion. Of course, this is now something we are familiar with. A body continues at rest or moving with a uniform speed or moving with a uniform velocity or uniform speed unless acted on by a resultant force. That is Newton's first law of motion. The variation with the time t of vertical speed v of a parachutist falling from an aircraft is shown in the figure here. So this is the graph. Actually, it is a graph of velocity against time. Remember, the gradient is acceleration. The area under the graph is displacement. So part A, calculate the distance traveled by the parachutist in the first 3.0 seconds. So we look for 3.0 seconds. Remember the scale on the vertical, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have 10 divided by 25 to get the scale on the x-axis. But since I want a time of 3 seconds, so 10 divided by 25, so one small square is 0.4. Now I want 3 seconds. So I will say 3 divided by 0.4. Those are 7.5 small squares. So I have 1, 2, 3, 4, 5, 6, 7.5. So 7.5, that's where I have 3.0 seconds. So, and you see it is 7.3 seconds is somewhere in the middle of this box. So it is at actually 30, velocity is 30, I guess. Or it is approximately 29.5. It could be somewhere here in the middle of the box. 29.5. Because the scale on the vertical is actually 1 meter per second. So since it is in the middle of the box here, it is somewhere here, it is 29.5. So that is 29.5 meters per second at 3 seconds. So distance is going to be the area under the graph. And you see it is a straight line. So distance is equal to the area under the line. So the distance is going to be area, which is a triangle, that is a half. What would have been like the base would be 3.0 seconds. This is in seconds. Times the vertical, what would have been like the height is 29.5. Remember, this is in meters per second. So you just press your calculator. So this is giving me 44.3 meters, 44.3 meters, or approximately 44 meters. Of course, I'm very certain some of you are short-sighted, so I would also accept answers such as somebody would see, especially on this value here, it could be a half times 3.0 times 29. For some people who may not be able to really see that is in the center, some people would estimate it as 29, which would give you a value of, I think, this is 29 times 3 divided by, that is 43.5 meters, which is approximately 44. Another person would estimate this to 30, around 30, and if you estimate it to 30, then it means you would have the distance as a half times 3.0 times 30, and I think this is exactly 45 meters. But the most appropriate is 29.5. Okay, explain the variation of the resultant force acting on the parachutist from t equals to 0, that is at point A, to t equals to 15 seconds at point C. So we are explaining the variation of the resultant force. Between t equals to 0 to t equals to 3, you see that the velocity is increasing by equal amounts in equal time intervals. That means the gradient is constant. The acceleration there is a constant value, and it is not 0. But I want you to notice that after 3 seconds, you see that it starts becoming a curve. which means, and it is a curve of decreasing gradient, which means the gradient is decreasing, which means the acceleration is decreasing. Remember, acceleration is directly proportional to the resultant force. Resultant force F is given by mass times acceleration. After 3 seconds, the gradient is decreasing, yet the gradient of a velocity time graph is the acceleration. So the acceleration after 3 seconds is decreasing, meaning that the force is also decreasing. At B, between B and C, it is a horizontal line, which means that the gradient is 0. And if the gradient is 0, it means the acceleration is 0 because the velocity is constant between B and C. And if the acceleration is 0, the resultant force is 0. At that point, because the parachutist is falling in air, then we can say that air resistance is actually balancing with the weight of the parachutist, and therefore the resultant force is going to be 0. So this is an easy question. Number 1, since we want to describe the resultant force, we can first of all note that the resultant force is the same as the weight minus the frictional force or the air resistance. It's the same as the the weight minus the frictional force which in this case is going to be the air resistance. So what happens when the speed increases? So air resistance increases with the speed. So air resistance increases with the speed. We know that air resistance increases with the speed. But at the start, air resistance equals to 0. At t equals to 0, air resistance equals to 0. And it increases until it balances with the weight. Until it balances with the weight. At this point, resultant force is 0. Okay, so you can explain it directly in terms of acceleration. Since the resultant force is equal to the weight minus the air resistance, between t equals to 0 to t equals to 3, we see that the acceleration is constant. The acceleration is constant simply because the speed is increasing with equal amounts in equal time intervals. So it means at that point the resultant force is constant. Then after 3 seconds, we see that of course the air resistance increases, and if the air resistance increases, remember the weight is constant, the weight does not change. If the air resistance increases, it means the resultant force is actually decreasing. When the air resistance balances with the weight, then the resultant force at that point is going to be 0. Describe the changes to the frictional force on the parachutist at t equals to 15 seconds at point C. The changes to the frictional force on the parachutist at t equals 15 seconds, point C. So what happens at exactly point C? You see at point C, we notice that now after point C, again the velocity decreases. What does that mean? It means the resultant force is greater, but this time in the opposite direction, which means that the frictional force has increased further. So the frictional force is actually exceeding the weight of the object. So here, the frictional force increases. The frictional force increases beyond the weight. How do we see this? From the graph, you see that after point C, the velocity is decreasing, which means it is because the frictional force has now exceeded the weight. So the body is actually decelerating. Okay, part 2. Between t equals to 15 and t equals to 22. Between t equals to 15 and t equals to 22, describe the changes to the frictional force. Then, of course, between point C and T, what do we see again? We see it is, of course, frictional force is increasing, but then this is a straight line. Frictional force increases, but between C and 22, where is 22? I think 22 seconds, could be around here. Because the scale here, every one box is 0.4, this is 20.8, 21.2, 21.6, 22 is here. That is at point E. So we see that from C to D, it is a straight line. That means although the frictional force increases, it is constant between C and D because the resultant force is going to be constant since you see it is a straight line. The deceleration here between C and D is constant. First of all, at C exactly, the frictional forces increased. The frictional force increased. It increased. That's why we now see the velocity starts decreasing. But then the frictional force, although it has increased, is now constant. It has increased, but now it is constant. It is constant at a higher value than the weight. That's why now the velocity decreases uniform by equal amounts in equal time intervals. The deceleration here is constant. Deceleration constant because it's a straight line. Then after D, after point D, we notice that now it is a curve, which means that the gradient is again decreasing. So we can say the deceleration is decreasing, which means it's because the frictional forces or the frictional force is decreasing because the frictional force is determining the deceleration. So we can simply say our frictional force is constant and then decreases. Frictional force constant up to D and then decreases. And then decreases until point E. So the frictional force is constant from between C and D, and then it decreases until point E. The mass of the parachutist is 95 kilograms. Calculate for the parachutist between t equals 15 and t equals 17 the average acceleration. T equals 15 and t equals 17 the average acceleration. We expect this to be a negative. Acceleration is going to be change in velocity divided by the time taken for that change. At t equals 15, we can check from the graph. At t equals 15, that is point C, the velocity is 50, and at t equals to 17, that is at point D, we see that the velocity is 20. So the final velocity is 20, the initial velocity is 50, so it is 20 minus 50. So the acceleration V2 is 20 minus 50, and the change in time there is 17 minus 15. And from my calculator, this is negative 15. That is negative 15. Calculate for the parachutist again between that time the average frictional force. Remember, this is a deceleration. The negative is showing a deceleration. So the average frictional force. Remember, the resultant force is equal to the weight minus the frictional force. The resultant force is the weight minus the frictional force, and we know that the weight is going to be mg. Weight is mg, and the resultant force is mass times acceleration. So we shall have that ma is equal to the weight, which is mg, minus the frictional force, Fr. Ma, the acceleration is 15, so ignoring the negative because the negative just shows a deceleration. So we shall have m is 95 times 15. That is the resultant force, which is of course in the opposite direction, should be equal to the weight, which weight is 95. The weight is 95 times 9.81 minus the frictional force. Now remember, it is a deceleration. What does that mean? Because it is a deceleration, remember the weight is downwards. And the air resistance is in the opposite direction, upwards, which means that actually the resultant force is upwards, but the motion is downwards. The resultant force is upwards, but the motion is downwards, which means the frictional force is greater than the what? The frictional force is greater than the weight. So this means, first get the weight here. Why can't I first calculate the weight? Because so the weight is equal to 95 times 9.81. Remember, the weight is downwards. 95 times 9.81, which is downwards, and this is going to be 95 times 9.81. This is approximately 932 newtons. That is the weight. Then, okay, let me just substitute directly. The resultant force is going to be M, which is 95, times acceleration. So let me just use the negative so that people will see that is a deceleration. So the resultant force is equal to 95 times negative 15, which is equal to the weight, which is 935, minus the frictional force, which I want to find, which I'm calling Fr. So 95 times 15. So I will say that this is negative 1425, equaling to 935, no, 932. 932 minus Fr. So when I collect like terms, it means frictional force Fr is going to be equal to 932 plus 1425. So this is giving me a total of approximately 2,357, or approximately 2,400 newtons. Okay, remember the minus sign here, which shows that is a deceleration, which indicates that the resultant force is actually in the opposite direction to the motion. So that means the frictional force plus the resultant force should be equal to actually the friction force plus the resultant force is equal to the weight downwards. That's why you notice that when I make Fr the subject, it means I get 932 plus 1425. That is, the friction force is going to be the resultant force plus the weight, since the resultant force is in the opposite direction to that of motion, which simply indicates that the body slows down instead of accelerating or speeding up. Okay, that is more abstract. State Newton's second law of motion. So the second law, that is F equals to ma, the net force is directly proportional to the rate of change of momentum. So I'll simply say net force or resultant force. The force here must be the resultant. So the net force is directly proportional to the rate of change of momentum, and in the same direction as the change in momentum. So the net force is directly proportional to the rate of change of momentum. Of course, we know that the resultant force and the change in momentum must be in the same direction according to Newton's second law. A ball of mass 65 grams hits a wall with a velocity of 5.2 meters per second perpendicular to the wall. So the ball hits perpendicular to the wall. Of course, we expect it to rebound also perpendicularly. So it rebounds perpendicularly from the wall with a speed of 3.7 meters per second. The contact time of the ball with the wall is 7.5 milliseconds. Calculate for the ball hitting the wall, the change in momentum. We know that momentum is going to be mass times velocity. So the change in momentum is going to be the mass, which is 65 grams. That is 65 times 10 power negative 3 Then the change, because there is rebounding, there is a change in direction, so this will be 5.2 minus negative 3.7. When I press my calculator, so from my calculator, this is 0.58. Then the magnitude of the average force. We know that by definition, force is equal to the rate of change of momentum. So the change in momentum is 0.58. Then the time of contact is 7.5 milliseconds. So that is 7.5 times 10 power negative 3. And from the calculator, so this is 77.3 newtons. For the collision in B between the ball and the wall, state how the following apply. Number 1, Newton's third law. Of course, we know when the ball collides with the wall, it exerts a force on the wall, and the wall will exert an equal but opposite force on the ball. So that is very easy. So the force on the wall, the force on the wall from the ball is equal but opposite to the force on the ball from the wall. So the force on the wall from the ball or by the ball is equal but opposite to the force on the ball by the wall or from the wall. That is Newton's third law. Then state how the following apply. The law of conservation of momentum. So how does the law of conservation of momentum also apply to that system of the ball and the wall? Of course, when the ball hits the wall, there is a change in momentum, and the change in momentum or momentum change of the ball should be equal but opposite to the change in momentum of the wall. Or the total change of momentum of the ball and the wall should be 0. That's why you see the wall is not moving, its initial momentum is 0. Although the momentum of the ball itself changes, the total momentum of the ball and the wall is supposed to remain as 0. So you can say the momentum change of the ball is equal but opposite to momentum change of the wall. Indirectly, we are relating the law of conservation of momentum to the ball and the wall. Alternatively, you can simply say total change in momentum of the ball and the wall is 0. Now somebody will say, but teacher, we calculated and we got the change in momentum 0.58. That was the change in momentum for the ball hitting the wall. So this is change in momentum for the ball, not the total change in momentum. So if the change in momentum for the ball is 0.58 in one direction, we can predict that the change in momentum for the ball should also be 0.58 in another direction, so that the total change in momentum will be actually 0. State with a reason whether the collision is elastic or inelastic. Of course, we see that the collision is inelastic because kinetic energy cannot be conserved for this ball. You see, for the ball, for kinetic energy of the ball was automatically 0. But you see, when the ball hit the wall, the relative velocity of approach was 5.2 minus 0. When it bounced, the relative velocity of separation is 3.7 minus 0. So that means kinetic energy is not conserved. So kinetic energy of the ball and the wall is not conserved. Kinetic energy of the ball and the wall is not conserved, so inelastic. Alternatively, you can look at the relative speed of approach and relative speed of separation. Relative speed of approach is not equal to the relative speed of separation. So inelastic. Okay, so that is why we are saying the collision is inelastic. The relative speed of approach is not the same as the relative speed of separation, so the collision is inelastic. State the principle of conservation of momentum. The total momentum of an isolated system of interacting bodies is always constant. I said isolated can be closed, and a closed system is the one on which no resultant forces is actually acting. So the total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting bodies is always constant. That is the principle of conservation of momentum. The ball X and the ball Y are traveling along the same straight line in the same direction as shown here. So we shall say velocities to the right are positive. All velocities are to the right, so that is going to be positive. Ball X has that mass 400 grams, velocity 0.865. Ball Y 600 grams, velocity 0.45. Ball X catches up and collides with the ball Y. After the collision, X has a horizontal velocity of 0.41 and Y has a horizontal velocity v. Calculate the total initial momentum of the two balls. Do not forget to write the formula. Momentum is equal to mass times velocity. So total momentum we are finding for both balls, so I have to change the masses into kilograms. So for ball X, mass is 0.4 times its speed, which is 0.65, plus ball Y, its mass is 0.6 times its speed, which is 0.45. From my calculator, this is 0.26 plus 0.27. Of course, when we add these two, we get 0.53. Then the velocity v. Of course, we are going to use conservation of momentum to find the velocity. By conservation of momentum, the momentum after collision should also be 0.53. So I'll just say total momentum after collision is 0.53, should be equal to, initial total momentum should be 0.53. But total momentum after collision, the mass is 0, x is 0.4. The speed is 0.41, plus for y, the mass is 0.6, the speed is v. So I'm going to simplify this. 0.4 times 0.41, I take the other side, minus, so 0.53 minus that. So v is going to be equal to 0.366 divided by 0.6. And this gives me 0.61. Then the total initial kinetic energy of the two balls. So we know that kinetic energy is equal to a half mv squared. Half mv squared. So we want total initial kinetic energy. Total initial kinetic energy is going to be for ball X, that will be a half. Its mass is 0.4. Its initial speed was 0.65, and this is squared. That is for X, plus for Y, that is a half. Its mass was 0.6. Its speed is initial speed from there, it was 0.45. So this will be times 0.45, and this is also squared. So this is 0.0845 plus 0.06075. Then when I add, so this is 0.145 joules. 0.085 plus 0.061. Yeah, 0.061. 145 joules. So 0.0145 joules. Explain how you would check whether the collision is elastic. How would you check whether the collision is elastic? So we look at the relative velocity of approach, which is going to be 0.65 minus 0.45, and that is 0.65 minus 0.45. So the relative velocity of approach is 0.2, and the relative velocity of separation is 0.41, and we got our value of V as 0.61. So we are going to subtract 0.61 minus 0.41. Since they're in the same direction, we just subtract. So 0.61 minus 0.41. And we are seeing that this is exactly 0.2. So you notice that the relative velocity of separation and the relative velocity of approach are the same. So the collision is going to be elastic. So the question was, explain how you would check whether the collision is elastic. So first of all, you can check whether the kinetic energy is conserved, or you check the relative velocity of approach and the relative velocity of separation. So check whether kinetic energy is conserved. Check whether the kinetic energy is conserved, or check whether the total kinetic energy before. Let me just change this. Check if total kinetic energy before collision is the same as the total kinetic energy after collision. Total kinetic energy after collision. And if they are the same, then the collision is elastic. Or you can check whether the relative speed of approach is equal to the relative speed of separation. If it is, then the collision is elastic. Use Newton's third law to explain why during the collision, the change in momentum of x is equal and opposite to the change in momentum of y. So we are using Newton's third law to explain why during the collision, the change in momentum of x is equal and opposite. So remember, by Newton's third law, the force on x should be equal but opposite to the force on y. But force is the rate of change in momentum, which means the change in momentum over time for x is going to be negative the change in momentum over time for y. But remember, the time of contact is the same, so t cancels out, which means that the change in momentum for x is equal to the negative change in momentum for y. The negative indicates that they are in opposite directions. So we can simply say that the force on x by y is equal but opposite. Is equal but opposite to the force on y by x. Force on x by y is equal but opposite to force on y by x. Remember, force equals to the rate of change of momentum. The force equals to the rate of change of momentum. That is a change in momentum over time. And the time is the same for both. And since time is the same for both, then change in momentum x is equal and opposite is equal and opposite to that of y. So that is using Newton's third law. A trolley T moves at a speed of 1.2 meters per second along a horizontal frictionless surface. The trolley collides with a stationary block on the end of a fixed spring as shown in the figure. So we see the trolley is moving towards the block which is attached to a spring. The mass of T is 250 grams, that is 0.25 kilograms. The mass of T is 250 grams. T compresses the spring by 5.4 centimeters as it comes to rest. Of course, it loses kinetic energy as the spring gains elastic potential energy. The relationship between the force F applied to the block and the compression X of the spring is shown by the figure here. So this is a graph of compression against the force. The force applied. As more force is applied to the block, that is of course by the trolley, by T, the compression also increases. This is not extension, it is compression. The compression is increasing. Use the figure to determine the spring constant of the spring. So that is very easy. The spring constant from Hooke's law, we know that force is equal to K times X. And it is a graph of X against F. So I can find since it goes through the origin, I can find a spring constant from F over X or from 1 over the gradient. That is 1 over the gradient. So I'll just take a value of F. So that is, since the scale on the x-axis is 0.2, that is 2 over 10. 0.2 is the scale on the x-axis. So that will be 4.4 divided by, I'm using this formula here, substituting the corresponding value of x, which is this one, and this is I think 5.4 because the scale on the vertical is 1 divided by 5, which is 0.2. So this is 5.4, but it is in centimeters, so that is times 10 power negative 2. So I'll check with my calculator. So from my calculator, I have that the spring constant is 81.48. You can also verify 81.48 newtons per meter. Then I again use the figure to determine the work done. The work done, of course, the work done is just going to be given by the area under that line. So work done is equal to the area under the line, or it is also a half F times X, or it can be a half Kx squared. Any of these will help you to find the work done. So area is going to be a half times, I'll take my value of F as 4.4 times the corresponding value of X, which is 5.4 times 10 power negative 2. That is also area under the graph. I think I'm writing too poorly. So from my calculator, So this gives me 0.119 or approximately 0.12 as the work done. Then the spring then expands and causes T to move in a direction opposite to its initial direction. At the time that T loses contact with the block, it is moving at a speed of 0.75 meters per second. That means it has been actually projected with that speed. But remember the work done, okay, it is projected with that speed. From the time that T is in contact with the block, describe the changes, the energy changes from the time that T is in contact with the block. When T gets in contact with the block, it is going to lose its kinetic energy as the spring gains elastic potential energy. So it means kinetic energy of T and the block becomes elastic potential energy of the spring. That means the kinetic energy of T is going to actually be smaller, it reduces. So we can simply say that the kinetic energy of T kinetic energy of T and the block, because we are looking at the time when the T is just in contact with the block. So this changes to elastic potential energy elastic potential energy. Of course, this is going to give a lower kinetic energy to the trolley, to give a lower kinetic energy to T. So of course, since part of the kinetic energy of the trolley, when it is in contact with the block, changes to elastic potential energy, then the trolley or T will have a smaller kinetic energy. Determine the change in momentum of T. Remember, momentum is equal to mass times velocity. So we want the change in momentum. The mass of T, what was the mass of T? I think was 250 grams, which is 0.25. Then the change in velocity. The change in velocity. Note that the block was, T was moving with a speed of 1.2 meters per second towards the block. But then they have told us that at the time that T loses contact with the block, it is moving at a speed of 0.7, because the spring then expands and causes T to move in the opposite directions. The spring then expands and causes T to move in opposite directions. So that means these velocities are in opposite directions. So initial velocity we can set was moving, set to the right, we can call that 1.7, 1.2 to the right initially, minus, then because it now moves in the opposite direction, so we shall say minus negative 0.75. So this is going to give us, from my calculator, so this is 0.49. Okay. A ball of mass 0.30 kilograms moves along a curved track as shown in the figure. So you see that it has some speed. At A it has that speed. The speed of the ball is 1.3 when it is at point A at a height of 0.31 meters. The ball moves down the track and collides with the vertical wall at point B. The ball then rebounds. The ball then rebounds back up the track. It may be assumed that frictional forces are negligible. Calculate the change in gravitational potential energy of the ball in moving from point A to point B. The change in gravitational potential energy. That is a simple question. We know that potential energy is mgh. So the change in gravitational potential energy is going to be mg times the change in height. So the mass of the ball is 0.03. So we shall say 0.03, that is the mass. G is 9.81. Then the change in height it's because it's falling downwards. The height is actually, the change in height is 0.31. So without wasting any time, I just press my calculator. And this is giving me 0.091 to two significant figures. Show that the ball hits the wall at B when its speed is 2.8 meters per second. So maybe we shall easily use the expression for kinetic energy, because we want to show that the ball hits wall B with that speed. So the kinetic energy at A, since we know that kinetic energy is equal to half mv squared, so the kinetic energy at A is equal to a half times the mass is 0.03 times 1.3 squared. This is the kinetic energy at A. From my calculator, so the kinetic energy at A is 0.0254. The ball has kinetic energy at A, and also it has potential energy at A. It is going to gain kinetic energy as it moves. It is going to lose potential energy. So it means the kinetic energy at A plus the change in potential energy should give us the kinetic energy at B. Because it has kinetic energy at A, it is going to just increase as it falls towards B. It is going to increase because there is a loss in gravitational potential energy. So it means the kinetic energy at A plus the loss in gravitational potential energy should give us the kinetic energy at B. So therefore, we shall simply say that kinetic energy at A, EK at A, plus the change in potential energy should give us kinetic energy at point B. Okay, so this means the kinetic energy at A, we have got it as 0.0254 plus the change in potential energy the change in potential energy when it reaches B, which is 0.091, should give us the kinetic energy at B, which is going to be a half times the mass, which is 0.03, times the speed at B, which I'm going to call V squared. That is times V squared. So let me sum up this. 0.0254 plus 0.091, then times 2, divide by 0.03, square root of the answer. So I'm finding V as 2.78 which is approximately 2.8 meters per second as the value of V. The change in momentum of the ball due to the collision with the wall is 0.096 kilogram meter per second. The ball is in contact with the wall for 20 milliseconds. Determine for the ball colliding with the wall the speed immediately after the collision. They have given us the change in momentum. And by conservation of momentum, the change in momentum determine for the ball colliding with the wall the speed after the collision. So the change in momentum is going to be the same, is actually going to depend on the change or difference in velocities. Let us assume the ball is colliding with the wall with that speed, which is 2.8, and it rebounds with the speed v. So the change in velocity is going to be v minus negative 2.8 or 2.8 minus negative v, whichever you consider to be positive. So I've started with v instead of 2.8, but I could still also say 2.8 minus negative v, assuming that I've considered it to be in the opposite direction. So the change in momentum is given, and we know that momentum is mass times velocity. So the change in momentum is 0.096, which is going to be equal to the mass, which is 0.30, into the change in velocity. So it collides with 2.8 to the right minus negative v to the left because it rebounds. So this helps us to find v. I will just press my calculator, I divide and make v the subject. So remember, this is minus negative, which becomes plus. That one becomes plus. So this is giving me v as 0.4. 0.4 exactly. Then the magnitude of the average force on the ball. Of course, we know that force is equal to mass times acceleration, or force is the rate of change of momentum. So since the change in momentum is 0.096, divide by the time of contact was 20 milliseconds, so that is 20 times 10 power negative 3. When I press my calculator, from my calculator, this is 4.8. State and explain whether the collision is elastic or inelastic. Of course, you already see that the collision is inelastic. The relative speed of approach was 2.8. The relative speed of separation is 0.4 because the other one is at rest. The wall is at rest, so its velocity is 0. So we can simply say inelastic. Inelastic reason kinetic energy is not conserved. Because the speed after collision is smaller, it decreases. Kinetic energy decreases. So it is not conserved. You can even check it. You can even try to verify. Total kinetic energy before collision, it was the kinetic energy at A, which we got as 0.0254 joules initially. Then after collision, we find the kinetic energy at B, which is going to be a half times 0.03 times No, before collision it is not this. Because it hits the wall with a speed of 2.8, then the kinetic energy will depend on that speed. That's with the kinetic energy with which it collides. But even though, since it rebounds with a speed of 0.4, of course, since the mass is the same and a half is the same for both, then the kinetic energy is not the same. So even if I don't calculate this, you can find out. Kinetic energy when it is just arriving is a half, 0.03 times 2.8 squared. Then the kinetic energy after rebounding is a half times 0.03 times 0.4 squared. So it means it is not conserved. Alternatively, you can look at the relative speeds of approach. The relative speed of approach is 2.8 minus 0. The relative speed of separation is 0.4 minus 0. So the collision is inelastic. In practice, frictional effects are significant so that the actual increase in kinetic energy of the ball from A to B is 76 millijoules. The length of the track between A and B is 0.60 meters. Use your answer in A to determine the average frictional force acting on the ball as it moves from A to B. So to find the frictional force, we shall find the work done against friction. Work done The work done against friction is equal to, they have told us that in practice, frictional effects are significant so that the actual increase in the kinetic energy of the ball in moving from A to B is 76 millijoules. That is the actual increase. But we see that the change in gravitational potential energy is 0.091. And we see that the change in gravitational potential energy is not the same as the actual increase in kinetic energy. So it means there is a difference, and the difference is the work done against friction. So this is going to be 0.091 minus 76 millijoules is 0.076. That's the work done against friction. And we know that work done is equal to force times distance, where force is going to be the frictional force. So the frictional force is going to be the work done, which is 0.091 minus 0.076 divided by the distance, which is 0.60. So from my calculator, the frictional force is 0.025 newtons. State the principle of conservation of momentum. I think we are now familiar with this. The total momentum of an isolated system of interacting bodies is always constant. Do not forget this part of an isolated system because it's what helps us to know that the momentum is conserved. Ball A moves with speed v along a horizontal frictionless surface towards a stationary ball B. We see that ball A has a mass of 4 kilograms and ball B has a mass of 12 kilograms. The balls collide and then move apart as shown in the figure. Ball A has velocity 6.0 at an angle theta to the direction of its initial path. Ball B has a velocity of 3.5 at an angle 30 degrees to the direction of the initial path of ball A. By considering the components of momentum at right angles to the direction of the initial path, calculate theta. So first of all, we know that momentum is mass times velocity. Momentum is mass times velocity. So we are going to consider components of momentum at right angles to the direction of the initial path of ball. In other words, we are going to consider vertical components. Initially, the balls are not moving in the vertical. So initial momentum in the vertical is going to be 0. But after collision, ball A moves in the vertical, it is moving vertically upwards, where we have to resolve this speed in the vertical, and that will be 6 sine theta. Ball B in the vertical will be moving downwards, so we have to resolve this speed downwards, and to be 3.5 sine of 30. So after collision, the momentum of A is going to be the mass of A, which is 4.0, times the speed after collision, which is 6 sine theta, plus, actually it will be minus because they are in opposite directions. For B, the mass is 12 times the speed is 3.5 sine of 30. So here you just simplify this. So this is 24 sine theta, which is equal to 42 sine of 30. So this means sine theta is going to be 21 over 24, which gives us theta as 61 degrees. Use your answer in Roman 1 to show that the initial speed v of ball A is 12 meters per second. So we want to find the initial speed v of ball A. So we are just going to conserve momentum in the horizontal. Initially in the horizontal, ball A was moving with a speed v. So we want to see that v is 12 meters per second. So total initial momentum in the horizontal is the mass, which is 4.0, times the velocity, which is v. The other one was at rest, momentum is 0, so this should be equal to, we are conserving momentum in the horizontal, so in the horizontal, A moves with a speed which is 6 cos theta, which theta is 61, and B moves also in the horizontal to the right in the same side, which with a speed which is 3.5 cos of 30. So we shall sum up those two. So this will be 4.0 times the speed, which is 6 cos theta, which is 61, plus, for the other one is 12 times 3.5 times the speed, which is 3.5 cos of 30. So simplify the right hand side. 4 times 6 cos 61 plus 12 times 3.5 cos of 30 divide by 4. So I'm finding V as 12.00002, which is approximately 12 meters per second. You can also verify. By calculation of kinetic energy, state and explain whether the collision is elastic or inelastic. So let's find total kinetic energy before collision. I'm calling it EK1. Remember, B was at rest, it is A which was moving. So this is a half times the mass of A, which is 4.0, times its speed, which is 12 squared. total kinetic energy, so that is 4 times 12 squared times divided by 2. So total kinetic energy here is 288 joules. Then kinetic energy after the collision, so it is a half times 4.0 times the speed of A after collision, which was 6. Do not resolve speeds when you are finding kinetic energy, plus a half times the other one has mass of 12 times its speed after collision, which is 3.5 squared. So this is giving me 145.5 joules. And you notice that the kinetic energy after collision is smaller than the kinetic energy before collision. So we see that kinetic energy is not conserved. So kinetic energy is not conserved. Kinetic energy is not conserved, so the collision is inelastic. Because kinetic energy is not conserved, the collision is inelastic. A wooden block moves along a horizontal frictionless surface as shown here. The block has a mass of 85 grams and moves to the left with a velocity of 2 meters per second. A steel ball of mass 4 grams is fired to the right. The steel ball, moving horizontally with a speed of 45 meters per second, collides with the block and remains embedded in it. So that means they move with a common velocity. After the collision, the block and the steel ball both have speed v. Calculate v. So we just conserve momentum. Momentum is equal to mass times velocity. Before collision, they are moving in opposite directions. So this for the first one, I will not change the mass because I'm going to equate on both sides. So the grams will cancel out. So I'll simply say 4.0 times its speed, which is 45, plus the other one is 85 times its speed, which is negative 2.0 because it's moving in the opposite direction, should be equal to, after collision they stick together, so the total mass is going to be 4 plus 85, then times the speed v. So this is going to give us 4 times 45 minus 85 times 2. So this side I have 10. 10 is equal to 89 V. So V is going to be equal to 0.112, or simply 0.11. Then for the block and the ball state, relative speed of approach before collision. So we just subtract. To the left it is 40, to the right is 45, minus to the left is negative 2. One direction positive, opposite direction negative. So it is 45 minus negative 2, which gives us this as 47. If they're in the same direction, you just subtract without minding about a negative. If they're in opposite directions, you subtract thinking about the direction. Then the relative speed of separation after collision. Since they stick together, the relative speed of separation is 0 since they move with the same velocity. Use your answers in Roman 1 to state and explain whether the collision is elastic or inelastic. So the collision is inelastic. relative speed of approach is not equal to relative speed of separation. So inelastic. When the relative speed of approach is not the same as the relative speed of separation, kinetic energy cannot be conserved, so the collision is inelastic. Use Newton's third law to explain the relation between the rate of change of momentum of the ball and the rate of change of momentum of the block during the collision. So first of all, the force on the ball by the block is equal and opposite to the force on the block by the ball. The force on the ball by the block is equal and opposite to the force on the block by the ball. Remember, force is equal to the rate of change of momentum. Force equals to the rate of change of momentum. In other words, remember, force is equal to change in momentum over time, but the forces are equal but opposite. And since time is the same, then the rate of change of momentum are equal but opposite. Since time of contact is the same, then the rate of change of momentum, let me say the rates because there are two, the rates of change of momentum are equal but opposite. Okay, so that is very easy. Do not forget the force on the block. The force on the block, I'll call it F1 maybe. Just to remind you, the force on the block, I'll call it F1, is equal but opposite the force on the block by the ball is equal but opposite the force on the ball by the block. So let's say F1 is equal to negative F2, but remember, force is the rate of change of momentum. So the change in momentum with the time of the first block is equal but opposite to the change in momentum over time by the second block. And it is the same. So change in momentum are going to be equal but opposite. State the principle of conservation of momentum. Now we are used to this. The total momentum of an isolated system of interacting bodies is always constant. The total momentum of an isolated system of interacting bodies is always constant. The propulsion system of a toy car consists of a propeller attached to an electric motor as illustrated here. The car is on a horizontal ground and is initially held at rest. initially held at rest by its brakes. When the motor is switched on, it rotates the propeller so that air is propelled horizontally to the left. The density of the air is 1.3 kilograms per meters cubed. Assume that the air moves with a speed of 1.8 meters per second in a uniform cylinder of radius 0.045 meters. Also assume that the air to the right of the propeller is stationary. Show that in a time interval of 2.0 seconds, the mass of air propelled to the left is 0.03 kilograms. So, first of all, we want to find the mass. And the mass of air is going to be the density of air times the volume of air. We know that volume, this is not small v, it is capital V for volume. We also know that volume is going to be equal to a cross-sectional area A times the height h. So the height h, remember this, the air is in a cylindrical, is covering a cylindrical area. I'll call this the height h, or the distance, I'll call it d. So volume is going to be cross-sectional area, which is pi r squared. To get h, or the distance d, is going to be equal to the speed times time. Speed times time. So that is going to be our volume. So to find the mass, therefore, mass is going to be the density of air, which is 1.3, times the volume of air, which is going to be pi, times the radius, which is 0.045, times the distance d or h, which is going to be the speed, which is 1.8, times the time. What was the time? Is 2 seconds. So this is 2.0 seconds. So I press my calculator. 1.3 times pi times 0.045 times 1.8 times 2. Oh, by the way, this is pi r squared. This is squared, times 0.045. So this is giving me 0.0298, approximately 0.030. Calculate the increase in momentum, the momentum of the mass of air in B Roman 1. Increase in momentum. So the increase in momentum is going to be the mass, since it is the mass which is changing, so it will be the change in mass times V, because the V is not changing. So this is going to be equal to the increase in mass, which is 0.030 times V, which is 1.8. So this is 0.054. Okay, so then calculate the force exerted on this mass of air by the propeller. So force is the rate of change of momentum. Change in momentum is 0.054 divided by time, which is 2.0. Time was 2.0 seconds. So just dividing this by 2, that is 0.027, I guess. Explain how Newton's third law applies to the movement of the air by the propeller. That is very easy. The force on the air by the propeller should be equal but opposite to the force on the propeller by the air. The force on air by the propeller is equal but in opposite direction to the force on the propeller by air. So that is Newton's third law. The total mass of the car is 0.2 kilograms. The brakes of the car are released and the car begins to move with the initial acceleration of 0.075 meters per second. Determine the initial frictional force acting on the car. Determine the initial frictional force acting on the car. First of all, we have the resultant force acting on the body, which can help us to find actually we have the force exerted on the mass of air by the propeller, which is 0.027. So that is the force, that is again going to be the force by the propeller. So the force of the propeller, the force, I'll call force of the propeller Fp, is going to be the same as the force of the mass of air on the propeller by Newton's third law. So the force by the propeller is 0.027 newtons. That's what we have found above. Then the force due to the frictional force, I'll call it Fr, but the resultant force F is given by mass times acceleration. The resultant force is mass times acceleration, which is 0.20 times the acceleration, which is 0.075, which is so this gives me 0.015 newtons. That is the resultant force. Remember, resultant force F, the resultant force is going to be equal to the difference between those two values, which is the force by the propeller minus the frictional force. If the force of the propeller is greater than the frictional force, then the body moves in the direction of the force of the propeller. So the resultant force F is equal to that. So the resultant force is 0.015, equal to the force of the propeller, which is 0.027 minus the frictional force Fr. So the frictional force Fr is going to be 0.027 minus 0.015. So just subtract here. Okay, so this is going to be 0.12 newtons. Is it what? 0.027 minus 0.015. So it is 0.012. 0.012. State Newton's second law of motion. Of course, we know now the second law is about the resultant force or the net force. So I simply say the net force or resultant force is directly proportional to the rate of change of momentum. The net force is directly proportional to the rate of change of momentum. Remember, the two act in the same direction. And the two act in the same direction. The net force is directly proportional to the rate of change of momentum, and the two act in the same direction. So that is Newton's second law. The net force is directly proportional to the rate of change of momentum, and the two act in the same direction. A toy rocket consists of a container of water and compressed air as shown in the figure here. Water is pushed vertically downwards through a nozzle by the compressed air. The rocket moves vertically upwards. The nozzle has a circular cross-section of radius 7.5 millimeters. The density of the water is 1000 kilograms per meters cubed. Assume that the water leaving the nozzle has the shape of a cylinder. So the water leaving has the shape of the cylinder, which has a radius is 7.5 millimeters and has a constant speed. So it means this distance here will be speed times time. Constant speed of 13 meters per second relative to the rocket. Show that the mass of water leaving the nozzle in the first 0.2 seconds after the rocket launch is 0.46 kilograms. We have done a similar question before. The mass is going to be density times volume. Each of us knows the density of water even though it has been given, but we know that I will call this distance L. So this will be density, volume is going to be pi r squared times the distance L. So this is going to be density times pi r squared, and L is going to be the speed times time. So the mass is simply going to be density, which is 1000 times pi. The radius is 7.5 times 10 power negative 3, and this is squared, times the distance L, which L is the speed, that is 13, times at the time, which is 0.20. 1000 times pi times 7.5 exponent negative 3 squared times 13 times 0.2. So this gives me 0.459, approximately 0.46 kilograms. Calculate the change in momentum of the mass of water in B due to leaving the nozzle. So change in momentum is going to be the change in mass times speed, because the speed is not changing, it is the mass changing. So this is going to be the change is 0.46 and the speed is 13. Answer times 13. So this is 5.97, which is approximately 6.0 Newton seconds. The force exerted on this mass of water by the rocket, we know that force is defined as the rate of change of momentum, which is 6.0 divided by 0.20, because the time was 0.20. So this is just half of that, which is giving me 30 newtons. State and explain how Newton's third law applies to the movement of the rocket by the water. That is very easy. The force on the water by the rocket is equal and opposite to the force on the rocket by the water. The force on water by the rocket the force on water by the rocket is equal and in opposite directions, or in opposite direction to the force on the rocket by the water. Part 4. The container has a mass of 0.4 kilograms. The initial mass of water before the rocket is launched is 0.7 kilograms. The container has a mass of 0.4. The initial mass of water before the rocket is launched is 0.7. So the total mass is 0.7 plus 0.4. The mass of the compressed air in the rocket is negligible. Assume that the resistive force on the rocket due to its motion is negligible. For the rocket at a time of 0.20 seconds after launching, show that its total mass is 0.64 kilograms. Note that 0.20 seconds after launching, it loses the change in mass is 0.46 as we have calculated above. It loses some mass. So show that its total mass is 0.6. So mass is going to be total mass before the change, that is 0.40 plus 0.70, but the change in mass is 0.46, so we shall say minus 0.46. And this is giving me automatically 0.4, that is 1 point something, 1.10 minus 0.46, that is 0.64 kilograms. That is total mass after launching, because the change in mass is 0.46. So we subtract 0.46. Then calculate its acceleration. Of course, resultant force, we know that resultant force, the resultant force F is mass times acceleration. But the resultant force is going to be the difference between the weight, the force exerted on the mass of water by the rocket minus the weight of the rocket, because the weight of the rocket is downwards, but the force exerted by the mass of water by the rocket is the same as the force which propels the rocket upwards. So the resultant force is going to be equal to the weight downwards minus, no, it's not the weight downwards, the force which propels the rocket upwards, which is 30 newtons. We calculated it as 30 newtons minus the weight. Because the weight is downwards. So it means the acceleration A is going to be 30 minus the weight of the rocket is equal to 0.64, because that is its total mass. 0.64 times g, which is 9.81, that is the weight. Then divide by this value of m, which is the mass of the rocket, which is 0.64. So we check 0.64 times 9.81, 30 minus the answer, divide by 0.64. So this is 37.1, 065, which is approximately 37. Define force. Define force. At this point, we now know that force is the rate of change of momentum. Force is the rate of change of momentum. Force is the rate of change of momentum. The ball falls vertically downwards towards a horizontal flow and then rebounds. So you see the velocities must be in opposite direction. The ball reaches the floor with a speed of 3.8. The ball is then in contact with the floor for a time of 0.081. The ball leaves with 1.7 meters per second. The mass of the ball is 0.062 kilograms. Calculate the loss in kinetic energy of the ball. So we know that kinetic energy is a half mv squared. So the loss in kinetic energy is going to be a half. The mass of the ball is 0.062. Difference is in v squared. So we have 3.8 squared when it is hitting the ground, minus, or hitting the floor, minus 1.7 squared. Do not first subtract the velocities and then square. That would be wrong mathematics. You would rather find the kinetic energy towards the flow and then kinetic energy away from the flow and you subtract. So from my calculator, this is 0.36. Determine the magnitude of the change in momentum of the ball during the collision. Remember, momentum is mass times velocity. We want the change in momentum. So change in momentum is equal to, the mass is 0.062. Then let's see the differences in velocity. Remember, one velocity is in the opposite direction to the other, so it will be a negative. Difference in velocity will be 3.8 minus negative 1.7. And from my calculator, this is 0.34. Show that the magnitude of the average resultant force acting on the ball during the collision is 4.2 newtons. Resultant force F is equal to the rate of change of momentum, which is going to be 0.34 divided by time. The time was 0.081. 0.081. And this is 4.198, or approximately 4.2 newtons. Use the information in Roman 1 to calculate the magnitude of the average force of the flow on the ball during the collision. The average force on the flow. Remember, when the ball is hitting the floor, there is a force exerted on the floor, which we have got as 4.2 newtons. That is the resultant force on the floor. But the ball has a weight, which weight is going to be given by mg. So the total force exerted on the floor is going to be the resultant force on the floor plus the weight of the ball. So this means the average force is going to be equal to 4.2 plus the weight, which is 0.062 times g, which is 9.81. That is the weight, mass times g. And this is going to be so this is giving me 4.8 newtons. Then the average force of the ball on the floor during the collision. This was the average force of the flow on the ball. The weight is downwards and the resultant force on the floor. Then the average force of the ball on the floor during the collision. Of course, this is given by Newton's third law. The two forces are going to be equal but opposite. So this is automatically 4.8 newtons. A spring is fixed at one end and is compressed by applying a force to the other end. The variation of the force F acting on the spring with its compression X is shown here. A compression of 0.045 meters produced when a force F1 on the spring. The spring has a constant of 800 newtons. Determine F1. So know that F is equal to K times X by Newton by Hooke's law. So F1 is equal to K, which is 0.045. No, that is X. F is equal to 800 times 0.045, which is automatically. So this is 36 newtons. Use the figure to show that for a compression of 0.045, the elastic potential energy is 0.81. We know that elastic potential energy is a half kx squared, or the area under the graph. So this is a half times k is 800, x is 0.045 squared. 0.045 squared times 800 divided by 2. So this is exactly 0.81 in joules. A child's toy uses the spring in A to launch a ball of mass 0.02 kilograms vertically into the air. The ball is initially held against one end of the spring, which has a compression of 0.045 meters. The spring is then released to launch the ball. The kinetic energy of the ball as it leaves the toy is 0.75 joules. The toy converts the elastic potential energy of the spring into the kinetic energy of the ball using the information in A Roman to calculate the percentage efficiency of the conversion. So the energy or the elastic potential energy is 0.81, but the kinetic energy is 0.72. That means not all the elastic potential energy has been converted into kinetic energy. So the efficiency, remember, efficiency is equal to the useful power output or useful energy output to the energy input. So this is 0.72 is what becomes kinetic energy, but 0.81 is what is elastic potential energy. So times 100. So this is giving me 89%. Determine the initial momentum of the ball as it leaves the toy. Initial momentum. So momentum, remember, is mass times velocity. Momentum is mass times velocity. But we have the kinetic energy. Kinetic energy is a half mv squared. So we can combine the two equations. So in terms of kinetic energy, I'll multiply both sides. So I have twice m times ek is equal to m squared times v squared. I'm just modifying this. So you notice that twice m times ek is equal to momentum squared. So momentum squared is equal to twice m times kinetic energy. And we have the mass of the ball as 0.02 kilograms. So since we want the momentum, so momentum is going to be the square root of 2 times 0.02. Kinetic energy is 0.772. So, or you can first use momentum. You can first use kinetic energy to find V. Then you use V, you substitute in the expression for momentum. Now I'll just use this directly. 2 times 0.02 times 0.72 square root. So when I find a square root, I'm getting that this is 0.1697, approximately 0.17. So 0.17. The ball in B lifts the toy at a point A and moves vertically upwards through the air. Point B is the position of the ball when it is at maximum height h. Above point A. Remember, at maximum height, velocity is 0. Don't forget that. Ball reaches maximum height at point B. Ball at A, kinetic energy is 0.75. The mass is that. The gravitational potential energy of the ball increases by 0.6. That is going to help us to find h, because we know the change in gravitational potential energy is equal to mg times the change in the value of h. So h is going to be the change in the gravitational potential energy, because the ball, the potential energy increases by that. So this is going to be 0.60 divided by mg, which m is 0.02 times g, which is 9.81. So this gives us so this is 3.1. Determine the average force due to air resistance acting on the ball for its movement from A to B. Note that the initial kinetic energy is 0.75. The change in gravitational potential energy is 0.6. So it has reached maximum height, and the change in gravitational potential energy is 0.60. Yet the kinetic energy is 0.72. Why isn't the change in gravitational potential energy equal to the loss in kinetic energy? So we know that the work done is equal to force times distance. So we need the work done against air resistance, which is going to be the difference in the kinetic energy and the change or the increase in the gravitational potential energy. So that means the force is equal to 0.72 minus 0.60 divided by the work done, divided by the distance, which is 3.1. So this is giving the average force as 0.039 newtons. When there is air resistance, the ball takes time t to move from A to B. When there is air resistance, that means it is going to reach the maximum height in a very short period of time because of air resistance. It decelerates very fast. State and explain whether the time taken for the ball to move from A to its maximum height will be more than, less than, or equal to t if the air resistance is not there. Of course, the time is going to be more if there is no air resistance. After, even the highest point will be greater if there is no air resistance. The deceleration is going to be smaller because there is no air resistance, so the resultant force on the ball is going to be small. So the time taken is more. Reason is very simple. If the ball is moving upwards, the weight is downwards. Air resistance is also downwards. Because it is moving upwards, the force due to air resistance is downwards. If there is no air resistance, this is going to be small. If there is air resistance, the resultant force downwards is bigger, which makes it to decelerate faster. But if there is no air resistance, the resultant force on the ball downwards is less. So resultant force on the ball is less than that with the air resistance. And remember, the resultant force is downwards. If there is no air resistance, the resultant force is less, and therefore the time taken, so time taken is more than t. It will take more time to reach the maximum height. Actually, even the maximum height will be higher since the air resistance is not there. The resultant force downwards is smaller than when there was air resistance. A ball consists of a solid sphere suspended by a string from a fixed point P as shown here. Okay, so we can try to think of the forces acting here. If I draw a vertical line here through this, there is a force here which is the weight, that is 0 point. The mass is, what is the mass? The sphere swings from side to side. At one instant, the sphere is at its lowest position x, where its kinetic energy is 0.8586 joules. Its momentum is 0.72 Newton seconds in a horizontal direction. That means a short time later, the sphere is at position y, where it's momentarily stationary at maximum vertical height h, above point x. The spring has a fixed length and negligible weight. Air resistance is also negligible. On the figure, draw a solid line to represent the displacement of the center of the sphere at position y from position x. Of course, displacement is maximum distance from, the shortest distance. So this will be just a horizontal, a straight line. For displacement, will be just a straight line from one center to the other point. So that would be the line to be just a straight line. I don't know why it is hard to draw a beautiful straight line here. Displacement is the shortest distance. So that would be a straight line. Okay. Show that the mass of the sphere is 0.3. So the mass is 0.3. They have given us the kinetic energy. They have given us the momentum. We are just going to combine the two. We know that kinetic energy EK is equal to a half mv squared. I multiply both sides by 2. And the m, so I have 2m times EK is equal to m squared times v squared. I multiply both sides by 2. Both sides by 2 and both sides by m. So you notice that momentum squared is equal to twice m times EK. I just use the shortcut. You can get two equations, one for kinetic energy, another one for momentum. So momentum squared, the momentum is 0.72 squared is equal to twice times the mass times kinetic energy, which is 0.86. 0.72 squared divided by 2 divided by 0.86. So I'm finding m as 0.30 kilograms. So m is 0.3, so this is 0.30 times gravity, which is 9.81. Calculate the height h. So they have given us that it reaches A short time later, the sphere is at position Y, where it is momentarily stationary at maximum vertical height. So if it's momentarily stationary, it loses the kinetic energy as it gains potential energy. So at the change in energy, the gain in potential energy must also be 0.86 joules because it loses kinetic energy since it momentarily stops. But the gain in potential energy is equal to mg times the change in vertical height. So the height h is going to be 0.86 divided by mg. M is 0.30 times g, which is 9.81. So this gives us 0.29 meters. Then the distance between point P and the and the center of the sphere is 0.93 meters. The distance between point P and the center of the sphere is 0.93 meters. Note that H is, I'll draw a horizontal line here. We have calculated H as 0.29. So we can find this distance here. That distance is going to be 0.93 minus 0.29. And that distance is very important. So we want to find, show that theta is 47. So show that theta is 47. If I consider the cos of theta is adjacent, which adjacent is 0.93 minus 0.29 over, of course, the hypotenuse is going to be the same as the length P to X, which is, this length is 0.93 because it's the same string. So this is 0.93. That is cos theta. So cos of theta is 0.93 minus 0.29 divided by 0.93. 0.93 minus 0.29 divided by 0.93, shift cos. So theta is equal to 46.5, which is approximately 47 degrees. For the sphere at position Y, calculate the moment of its weight about point P. For the sphere at position Y, its moment of the weight. So we need, moment is force times perpendicular distance. So we need this distance here, perpendicular distance of the weight from perpendicular distance of the weight from point P, because we are taking moments about point P. So this is opposite. Remember, this distance here is the same as this distance. So opposite hypotenuse, I think that is sine. So this distance here, that distance D is going to be equal to 0.93 sine of 47, because it's opposite over hypotenuse. So sine theta is opposite, which is the distance we want, over hypotenuse, which is 0.93. So D is 0.93 sine theta, which theta is 47. So by taking the moments, so the moment is going to be the weight times 0.93 sine of 47, that is perpendicular distance, or you can take weight times 0.93 cos. The sine of 47 is the same as the cos of 43. But this one is the easiest because we see it on the diagram. So the weight is 0.3, that is the mass, times acceleration due to gravity, 9.81, that is mg, then times 0.93 sine of 47. So from my calculator, I get the moment as 2.0 Newton meters. State and explain whether the sphere is in equilibrium when it is stationary at position Y. Of course, we have already got a moment. There is no way it can be in equilibrium because it has moment. So there is a resultant moment, not a resultant moment. Okay, there is a resultant moment. There is a resultant moment about P. There's a resultant moment about P acting perpendicularly, or acting on the pendulum, or acting on the mass. There is a resultant moment about P acting on the sphere. So, not in equilibrium. Alternatively, there is a resultant force acting on the sphere, so it is not in equilibrium. Since there is a resultant moment, we also believe that there is a resultant force acting on the sphere. And of course, that resultant force is acting towards equilibrium position. So there is a resultant force so not in equilibrium. Okay, so that is, it is not in equilibrium. The ball is thrown vertically downwards to the ground with an initial speed u as illustrated there. The ball is thrown with a speed u from a height of 1.5 meters. The ball then hits the ground with a speed of 8.7. Assume that air resistance is negligible, calculate the speed u. So initial, we shall just use the equations of motion. If air resistance is negligible, then it is the acceleration due to gravity that is acting. And it is thrown vertically downwards. So v squared equals to u squared plus 2as. I think that will work. So that means u squared is going to be v squared minus 2as. So u squared is equal to v squared, which is 8.7 squared minus 2, 9.81, s is 1.5. So then we get u. So for my calculator, u is 6.8. State how Newton's third law applies to the collision between the ball and the ground. This is almost the same question every time. So the magnitude of force on the ball by the ground is going to be equal and opposite to the force on the ground by the ball. So magnitude, or just the force, magnitude of the force on the ball by the ground is equal, and in opposite direction, to the force on the ground by the ball. The ball is in contact with the ground for a time of 0.091 seconds. The ball rebounds vertically. It rebounds. You have that in mind. So if it rebounds, then the speed must be assigned a different value, a different sign. Calculate the magnitude of the change in momentum of the ball during the collision. So momentum is mass times velocity. The change in momentum is the mass. The mass is 0.059 times the velocity. It was falling with a velocity of 8.7, then it rebounds with a velocity of 5.4. So the difference is 8.7 minus negative 5.4. So I press my calculator. So from my calculator, this is 0.83. Determine the magnitude of the average resultant force that acts on the ball during the collision. We know that resultant force F is the rate of change of momentum. So this is going to be 0.83 divided by the time was, the time is 0.091. And from my calculator, this is 9.1. Use your answer in C Roman 2 to calculate the magnitude of the average force exerted by the ground on the ball during the collision. The average force exerted by the ground on the ball during the collision. So first of all, the resultant force is 9.81. And resultant force is the difference between the force exerted by the ground on the ball upwards minus the weight downwards. So first of all, the weight is m times g, which is 0.059. That was the mass, times g, which is 9.81. And this is 0.059 times 9.81. The weight is 0.58 newtons. But remember, resultant force is going to be the force by the ground, because the ground exerts a force on the ball upwards. The force by the ground minus the weight will be downwards. That is the resultant force, which means that now the resultant force, remember, is 9.1. This is the force by the ground. I'll call it force ground minus the weight, which is 0.58. So that means the force exerted by the ground is going to be 9.1 plus 0.58. Remember, this is the ground, the ball is falling, its weight is downwards, and the force by the ground is upwards. The resultant force is 9.81. So this means this is going to give us 9.1 plus 0.58, that is approximately 9.7 newtons. The ball was thrown downwards at time t equals to 0 and hits the ground at time t equals to t. Sketch a graph to show the variation with the speed of the ball when t with time t from t equals to 0 to t equals to numerical values are not required. Remember, air resistance was negligible, meaning that the acceleration was constant. And if the acceleration was constant, then the speed was increasing by equal amounts in equal time intervals. So that is a straight line, obviously. So that is going to be a straight line. So that is going to be a straight line. Of course, initial velocity, remember, was not 0, so it does not start from the origin. So this is going to be a straight line with a non-zero. So remember, it starts with some speed. Then the speed here was 8 point something, 8.7. So it is a straight line because air resistance was negligible. So it is going to be a straight line starting from a non-zero value of speed at t equals 0 and to end at t equals to t. In practice, air resistance is not negligible. State and explain the variation, if any, with the time t of the gradient of the graph in D when air resistance is not negligible. So what happens to the gradient? State and explain the variation, if any, with the time t of the gradient of the graph in D when air resistance is not negligible. Remember, if air resistance is negligible, air resistance increases with the speed. And if air resistance increases with the speed, it means the acceleration decreases. So the gradient of the graph will not be constant, but it would rather decrease. So air resistance increases with the speed. And if air resistance increases with the speed, it means the resultant force or the acceleration decreases. And if the acceleration decreases, it means the gradient, instead of it being a straight line, it will now become, the gradient will go on decreasing. So the gradient of the curve decreases. The gradient of the curve decreases. Okay. Define momentum. Of course, momentum is mass times velocity. There is nothing much to write about the definition of momentum. Product of mass times velocity. Two balls x and y of equal diameter but different masses, 0.2 kilogram, 4 kilograms, 0.1 kilograms, respectively, slide towards each other on a frictionless horizontal surface as shown here. So you see this is with a speed of 2.3, but this has mass which is twice the other. Both balls have the same initial speed before they collide with each other. The figure shows the variation with the time t of the force Fy exerted on ball y by ball x during the collision. So this is the force exerted on ball y by x during the collision. I think this is at 3. calculate the kinetic energy of the ball X before the collision. Of course, we know that kinetic energy is a half mv squared. So this is going to be a half. The mass ball X was 0.24 times the speed is 2.3 squared. So kinetic energy is so this is 0.63. The area enclosed by the lines and the time axis represents the change in momentum of ball Y during the collision. Determine the magnitude of the change in momentum of ball Y. So we just find the area, since they say the area enclosed represents the change in momentum. So this is a triangle, and the area of a triangle is going to be a half times the base times the height. The base will be now 5, and the height is going to be, what is this value for the height? I think this is 240, because on the scale is 200 divided by 10, which is 10. Yes? No, 200 divided by 10, which is 20. The scale on the vertical is 20, so this is 240, that is the height. So the change in momentum is represented by the area according to the question. So the change in momentum is going to be a half times what would be the base 2.0 times 10 power negative 3, because it is in milliseconds. This is seconds. When I multiply by 10 power negative 3, that is now seconds, times what would be like the height is 240, and it is in newtons. So this gives us Newton seconds. Then I multiply. So the answer here I'm getting is 0.60. Calculate the magnitude of the velocity of ball Y after the collision. So we have the change in momentum of ball Y. We now want the magnitude of the velocity after collision. So change in momentum of Y is 0.60. Change in momentum is equal to mass times change in velocity, let's say V2 minus V1. And they have given us the change in momentum as 0.6. So 0.60 is going to be the mass of ball Y. The mass of ball Y is 0.12. So change. So this is 0.12 into the change in velocity V2 minus V1. So we want to calculate the magnitude of the velocity of the ball after collision. Remember, its initial velocity was 2.3. V1 is 2.3. So I will have that 0.60 divided by 0.12 is equal to its velocity after collision minus its initial velocity, which is 2.3. So assuming that velocities to the left were negative, so this will be minus negative 3. If velocities to the right are positive, so this will be minus negative 3. So I just find V2. Remember, this will now becomes plus. So V2 is going to be equal to, I think this is 0.5, 5.0. 0.6 divided by 0.112, that is 5. 5.0 minus 2.3, which is 2.7. So V2 is going to be 2.7. Remember how why I brought in the minus? Because ball Y was moving to the left, and I'm assuming velocities to the left are negative, velocities to the right are positive. On the figure, sketch the variation with the time t of the force Fx exerted on ball X by ball Y during the collision. Of course, the force on ball X by ball Y is equal but opposite to the force on ball Y by ball X. So since the forces are in opposite directions, remember for Y the force is like this. Then for X is just going to be the mirror image of this because they are equal but in opposite directions. So the same graph but on the opposite side of the x-axis. So this is going to be below the x-axis. Remember this was 2240, so they could add 3. At 3 here, it should be 240. I'll just increase the weight. So this will be a straight line. So that will be the graph. Just the same as the one for Fy, but on the opposite. They are meeting here at 3 on the opposite direction, on the opposite side. Okay. A jet of water hits a vertical wall at right angles as shown here. Because it hits a vertical wall, we expect it to rebound at right angles. The water hits the vertical wall with a velocity of 5 meters per second, the horizontal direction. The cross-sectional area of the jet is 1.5 exponent negative 4. The density of water is 1.0 exponent 3. The water runs down the wall after hitting it. It runs down the wall. That means it does not rebound. Show that over a time of 1.6, the mass of water hitting the wall is 1.2. So know that mass is density times volume. All that we need is the volume. Because we have the density, all that we need is the volume. The density is 1000. For the volume, they have given us the speed and they have given us the cross-sectional area of the jet, and we now have the time. So this is going to be density, the volume is going to be the cross-sectional area, which is pi r squared times L, assuming it is cylindrical. So this will be density times pi r squared, where there is L, I'll have the speed or the velocity times the time. That will give us the length L of the water jet. So the mass is going to be equal to density, which is 1.0 times 10 power 3 times pi times, they gave us the cross-sectional area, so we don't need to find pi r squared. The cross-sectional area is 1.5, that is pi r squared will be 1.5 times 10 power negative 4, then times L, which is, because it's cylindrical, L is velocity, which is 5.0 times time, which is 1.6. So I'll check my calculator. 1 exponent negative 3 times 1.5 exponent negative 4 times 5 times 1.6. So this gives me 1 point, no, times 10 to the power 3 times 5 times 1.6. So this is 1.2. 1.2 kilograms. Calculate the decrease in the horizontal momentum of the mass of water in air due to hitting the wall. Decrease in the horizontal momentum. We know that momentum is mass times velocity. So the decrease in the horizontal momentum, since the mass is 1.2 and the velocity is 5.0 meters per second. So the decrease, this is going to be actually the change in the mass. So the decrease is going to be 1.2 times 5.0, which gives us, I think this is 6. So that is 6.0 Newton seconds. Then calculate the magnitude of the horizontal force exerted on the water by the wall. By definition, we know that force is equal to the rate of change of momentum, which is 6.0 divided by the time was 1.6, which gives us 6 divided by 1.6, that is 3.75, approximately 3.8 newtons. Then state and explain the magnitude of the horizontal force exerted on the wall by the water. This was the magnitude of the horizontal force exerted on the water by the wall. By Newton's third law, it is going to be the same. So because they said state and explain, so by Newton's third law, I will start by explanation. By Newton's third law, we know that the force exerted by the water on the wall should be equal but opposite to the force exerted on the wall or on the water by the wall. The force exerted by the water on the wall should be equal to the force exerted on the water by the wall. So by Newton's third law, the force is 3.8 newtons. Or you just say Newton's third law applies. Maybe that would be the best way of writing this. I'll say Newton's third law applies. Newton's third law applies. So the force is 3.8 newtons. Calculate the pressure exerted on the wall by the water. Pressure is the force acting normally per unit area. And we have seen that the force is 3.8 newtons. Then the area over which it acts is the same as the cross-sectional area of the water jet. So that means the area is 1.5 times 10 power negative 4. And this gives us, so this gives me 2.5 times 10 power 4 pascals. Okay. Define velocity. Of course, we now know velocity is the rate of change of displacement. Rate of change. Rate of change of displacement. That is velocity. Rate of change of displacement or change in displacement over time. That is velocity. A rock of mass 7.5 kilograms is projected vertically upwards from the surface of a planet. The rock leaves the surface of the planet with a speed of 4.0 meters per second at time t equals to 0. The variation with the time t of the velocity v of the rock is shown in the figure. So this is a graph of velocity against time. Remember, the gradient is acceleration, and the area under the graph is displacement. So this is starting at 4, and it crosses at 2.5, I think that is 2.5, and this value here is negative 2.4. Yes, because the scale on the vertical is 0.2. So that is negative 2.4. So let's start the questions. Assume that the planet does not have an atmosphere and that the viscous force acting on the rock is always zero. That is, friction is zero. Determine the height of the rock above the surface of the planet at time t equals to 4.0 seconds. Since we want to find the height, that is distance, and we know that distance or displacement is going to be the area under the graph. Displacement equals to the area under the graph. So the height is now going to be the displacement. When you look at this graph, you notice that between t equals to 0 to t equals to 2.5, the rock is moving upwards. It is moving upwards because the velocity is decreasing. So at 2.5, it has reached the highest point. So we find the displacement or the distance in that direction. Then after 2.5 seconds, it is now moving in the opposite direction. So we have to subtract this area here, so that we find the height above as required. So the height is going to be the area, which is a half, times the time is 2.5 times 4.0, that is in one direction. This is the first area of this part here. Then the other area is in the opposite direction, so we shall subtract. So we shall say minus a half times. Of course, the base here, what will be like the base is from 2.5 to 4. That is 4 minus 2.5, which is 1.5. This time interval is 1.5. So this will be minus a half times 1.5 and times the height, which is 2.4, because we found this as 2.4 here. This height here is 2.4. So now we just simplify this. I just find the answer here. So this is giving me 3.2. Determine the change in momentum of the rock from t equals to 0 to t equals to 4 seconds. Note that the velocities are in opposite directions. There is a change in velocity. Momentum is equal to mass times velocity. So we want the change in momentum. The mass is, I think the mass is 7.5. Let me check again. The mass of the rock is 7.5. So that is fine. So the change in momentum is 7.5 into so the velocity determine the change in the momentum of the rock. So initially the rock is moving upwards, and then because the velocity changes direction, so then that would be I would say 2.4. I would say 4 minus negative 2.4 because there's a change in direction, and this is going to give us That is 48. So the change in momentum is 48. Determine the weight W of the rock on this planet. So we wait to find the weight. Weight will of course be the force exerted, because the others are negligible, so it is just going to be the force exerted, which is going to be the rate of change of momentum. So this will be the change in momentum 48 divided by the time. What was the time? Between t equals 0, t equals 4, so the time is 4.0. So that is 4.0, and that is, I think that is 12. So the weight is going to be 12 newtons. Alternatively, you could find the weight from mg, and of course you would find this as m, which is 7.5, times g, which is 1 point, I think it is 1 point, isn't it 1.6, because that is 4 minus 2 point, g is going to be 4 minus 2 minus negative 2.4 divided by 4.0, which is, I think, 1.6. So that still gives you 12 newtons. In practice, the planet in B does have an atmosphere that causes a viscous force, in others that causes a friction. State and explain the variation, if any, in the resultant force acting on the rock as it moves vertically upwards. As it moves vertically upwards, we have seen that the speed is decreasing according to the graph. Air resistance decreases as the speed decreases, or the viscous force or friction force decreases if the speed decreases. In the first part, when it is moving upwards, the speed decreases. It means the viscous force decreases. And if the viscous force decreases, remember the weight does not change. It is moving upwards, the weight is downwards, the viscous force is also downwards, or the force due to air resistance is downwards. If it is moving upwards, the force due to air resistance decreases since the speed decreases. When this becomes smaller, the resultant force downwards is also smaller. Because the weight does not change, F due to air resistance reduces, the total of these two becomes smaller, so the resultant force reduces. Okay, so it shall simply say the speed decreases, speed decreases. We see that the speed is decreasing as it is moving upwards. Speed decreases, so the viscous force decreases. Remember, air resistance decreases with the decrease in speed. It increases with increase in speed. And here the air resistance is what we are calling the viscous force or friction force. So the viscous force decreases. Remember, the weight remains constant. Since weight is constant, resultant force decreases. I want to remind you of this. The rock is moving upwards. This is motion. But the weight of the rock is downwards. And if it is moving upwards, the viscous force is also downwards. So these two form the resultant force. Because it's moving upwards, the speed decreases. If the speed decreases, viscous force reduces, because viscous force of friction or resistance depends on the speed. And if the viscous force reduces with the weight not changed, it means the sum of the weight and the viscous force reduces, which is the resultant force. So the resultant force decreases. Okay. State, I think this is the last question. State the principle of conservation of momentum. So we now know that total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting bodies is always constant. Two balls X and Y move along a horizontal frictionless surface as shown from the figure 4.1. So this is not to scale. Ball X mass 3.0, velocity 4.0 in the direction at an angle theta to line AB. Ball Y mass 2.5, velocity 4.8 at the same angle theta as shown above. The balls collide and stick together, so they move in the x direction with the same speed. The balls have velocity 3.7 along the line AB on the horizontal surface by considering components of momenta along line AB. So that means in the horizontal. Calculate theta. So momentum is equal to mass times velocity. So we are going to conserve momentum in the horizontal. Ball X initially will have a velocity in the horizontal, which is going to be 4 cos theta. Ball Y will also have a velocity, which is 4.8 cos theta, and both will be in the same direction, so their total momentum will be summed up. When they collide, total momentum is going to be the sum of these two masses times that velocity in the horizontal. So we shall have 3.0 times 4.0 cos theta plus 2.5 times 4.8 cos theta should be equal to, after collision they stick together, so total mass is 2.5 plus 3.0, then times the common speed 3.7. So this is, I think this is 12, this is also 12, so that means this is 24 cos theta, and this would be 2.5 times 7 plus 3 times 3.7, this is 20.35. So theta equals to 20 divided by 24 divided by 24 cos inverse. So this is 32.01. So this is 32. That is 32. By calculation of kinetic energies, state and explain whether the collision of the balls is inelastic or perfectly elastic. So you can find initial kinetic energy. We know kinetic energy is a half mv squared. So let's find EK1. Initial kinetic energy before collision will be a half times the mass of the first ball, 3.0. Its speed is 4.0 squared plus. Remember, we don't resolve the velocities when we are finding kinetic energy. The second one is a half. Its mass is 2.5 and its speed is 4.8 squared. So that gives us the total energy. So this is giving me 53 joules. You can verify. Then kinetic energy after, the final kinetic energy, I will call it EK2. After the collision, they stick together, remember? So this is a half. Total mass is the sum, which is 2.5 plus 3.0. That is total mass. They move with the same speed of 3.7, so times 3.7 squared, which is equal to, this is 3.0, and I'm getting 38 joules. So the collision is inelastic because initial kinetic energy is not equal to final kinetic energy. Initial kinetic energy is not equal to final kinetic energy. So inelastic. Okay, so that marks the end of dynamics, and we shall meet in waves. I think waves is the most important unit here. So let's meet in waves. Enjoy your day. I hope this was helpful. If there's any problem, you can always raise it. I'm always bound to make errors. Thank you for watching this. Bye bye.